When a zero-day vulnerability breaches the deep hardware level of an enterprise system, the threat profile changes instantly. We are specifically looking at a scenario where a trusted execution environment, or TEE, vulnerability compromises the hardware trust boundaries of a CPU or GPU. Standard IT software incidents are typically managed by isolating the network, patching code, and rebooting. For hardware-level threats, that pipeline is insufficient. The unique challenge of a TEE breach is that the hardware designed to physically isolate and protect the system is the exact component that is no longer trustworthy. This hardware scenario requires the TEE Vulnerability Incident Response Protocol, a specialized countermeasure for high-assurance environments. This flowchart operates as a strict deterministic algorithm. Because each step depends on the cryptographic state of the previous one, there is no margin for parallel execution or skipped nodes. The protocol's primary objective is the systematic quarantine of decentralized hardware across an enterprise footprint, while maintaining a continuous audit trail. To achieve this, the response begins at the cryptographic boundary, isolating the system's ability to access sensitive secrets before addressing the compute layer. This means securing the key management layer takes priority over the immediate suspension of active workloads. By prioritizing cryptographic isolation before hardware remediation, the protocol prevents further data leakage while the root of trust remains compromised. Execution begins with immediate intelligence triage. Security teams compare the enterprise's active hardware and firmware versions against the specific parameters outlined in the CVE intelligence report. This decision gate evaluates the infrastructure. On the right, the topology map identifies which specific nodes fall within the high-risk radius of the vulnerability. Hardware categorized outside the risk radius remains in production, but is shifted into a state of active, logged monitoring. For nodes confirmed to be within the high-risk zone, the protocol shifts to aggressive containment. At this stage, engineers are directed to leave the running workloads untouched, while the isolation of the cryptographic layer is finalized. The first mandated containment action is the immediate update of the Key Management Service, or KMS, blocking policy. Watch the KMS server. The policy update severs external trust, creating a barrier that prevents cryptographic keys from reaching the compromised compute nodes. Mechanically, halting these key releases starves the high-risk hardware of the secrets required to maintain or spin up secure environments. Severing the key pipeline caps the blast radius by preventing any new secure enclaves from being provisioned on the vulnerable hardware. With the KMS blockade in place, the focus moves to the compute layer. The next sequential directive is the suspension of high-sensitivity inference tasks currently running on the affected hardware. These AI workloads are paused in their current execution state, but the compute instances themselves are kept intact. This preservation is required for a critical forensic phase that must be completed before any physical patching or reboots. The flowchart requires engineers to first export the comprehensive lists of all affected tasks. Simultaneously, the system exports the cryptographic receipts associated with those tasks, routing them to a secure, isolated logging server. These receipts provide mathematical evidence of the enclave's integrity and state during the specific window of execution. This forensic data must be moved off-node immediately, as the subsequent firmware updates and reboots will clear the volatile memory where this state resides. Exporting these receipts provides the evidence required to definitively track what sensitive data was processed during the vulnerability window. Once the forensics are secured, the protocol moves into the physical remediation phase. TEE vulnerabilities require updates across the entire stack, including hardware microcode, device firmware, OS images, and GPU drivers. These deep stack patches are deployed across all suspended high-risk nodes. In a zero-trust hardware environment, the successful deployment of patches does not restore the node's standing within the network security policy. The mandatory gateway to recovery is establishing a brand new attestation baseline. Until this baseline is established, the patched hardware remains untrusted by the enterprise network. The updated hardware node calculates a new cryptographic hash representing its current microcode and firmware state. This measurement is then transmitted to register with a central verifier. By formally registering this new mathematical measurement, the enterprise defines the new parameters for the root of trust. Central verifiers will now interrogate these nodes in real time, requiring them to match this specific registered baseline before allowing any network communication. Because the KMS requires a valid cryptographic measurement for all key releases, The node remains operationally inert until this new baseline is registered. In the final stages of the flowchart, the process moves from engineering execution to governance and authorization. The incident response package is handed over to security and legal oversight teams for a final risk assessment. This evidence package combines the new attestation baseline with the exported cryptographic receipts. The flowchart cannot progress to the final node until this package passes the security and legal approval gate. The legal team uses the exported receipts to evaluate historical data exposure and confirm regulatory compliance. Simultaneously, the security team verifies the new attestation baseline to ensure the hardware is effectively shielded against the known CVE. Formal authorization for service restoration is granted only once these security and legal thresholds are mathematically proven. Once authorized, the KMS policy is unblocked across the cloud infrastructure. The cryptographic barrier drops, and secure keys are released to the patched nodes. High-sensitivity workloads resume on the verified hardware, bringing the node back into full production. The recovery depends on a clear dependency chain, cryptographic quarantine, forensic export, deep stack remediation, and finally, re-attestation. In zero-trust environments, incident response moves from the software layer to the mathematical layer, requiring a formal, verifiable proof that trust has been restored.